Yeah, thanks for inviting me. Has been a very enjoyable conference so far. I hope I will not destroy this impression by my talk. So, but what will you have to expect? So I'm trying to give a somewhat lopsided introduction to homotopy type theory. Essentially, I mean, some people say that Martin Hofmann and I were sort of precursors, but we had very different motivations. So the first part of the talk will be to explain how we arrived at those considerations, in particular the Groupoidmodel, which can be understood as a precursor of homotopy type theory. Maybe a word on the funny two signs at the end of the title. So isomorphic types are equal has to be said with some emphasis because it's against evidence when you are a normally trained mathematician. That's the reason why there is an exclamation mark. I insisted on adding a question mark because I think it's something which has to be discussed but isn't discussed that much. In case I'm fast enough, I might spend a couple of minutes at the end commenting on, on this controversial issue, how I see it. Okay, good. But that's coming later. So, what is the motivation for something like saying that isomorphic type are equals? People think that it's a consequence of modern 20th century, well, maybe 20th century is not too modern anymore, but it was once, yeah. So what I mean with modern mathematics is structure-oriented mathematics, which developed when people were studying things like topology or geometry in the modern sense. And then, the impression came up that morally isomorphic structures are sort of equal. Well, I mean, if you look at it from the point of view of usual foundations of mathematics, it's blatantly wrong, because if you have an element x in A, and you A and B are isomorphic via some isomorphism I, I tried to use this pointer. Oh yes, isomorphism, yeah. And you have x in A, then it's in general absolutely wrong that Ix is in B. For example, you could take for A the odd natural numbers, for B the even natural numbers. They are in bijection. One is in the first set, but not in the other. So it has to be understood in the sense that not X is in B, but I of X is in B. In this sense, you can, in this sense, it holds. Now, verbatim, it's certainly wrong, because of the counterexample I gave. Now, the other thing is that when people are doing category theory or working in related fields, just for convenience, they pretend that isomorphism is the same as equality, so they miss to do a bookkeeping of following the ISOs they are using. Yeah, this is suppressed, so you just omit this I. And well, sometimes you can make mistakes, but most of the time it's okay. And so one may consider so-called intentional Martin-Löf type theory as a way enforcing this discipline. So my point of view is that what we have said here, if A is isomorphic to B and X is in A, so in general, it's wrong that X is in B, but it's right that I of X is in B. Now, On the next slide, I will recall what precisely the mechanism of identity types in Martin-Löf type theory, but in any case, there is no point of hiding this fact when you work with identity types in Martin-Löf type theory. You have to abandon certain habits which were followed from Euclid to before type theory, so from, well, n years before Christ, 350, I don't know, till 1930 at least, there was no problem with equality. In particular, you can replace equals in arbitrary formulae. But this is not the case in intentional Martin-Löf type theory, but there you always have to replace T along some equality proof. That means the mechanism how Martin-Löf type theory deals with equality essentially forces you to always have a fairly bureaucratic bookkeeping along which equality proofs you replace equals by equals. So it's not that isomorphic types are really equal in the sense of the equality we have used up to 1970 or even a bit longer, and most people still use this. It's rather that we have a different treatment of equality which enforces you to keep this discipline. When you really express yourself in Martin-Löf type theory, you cannot commit this sloppiness which you would do happily as a working category theorist. Right. So let me, oh yes, it works, brilliant. So here you have a very boring slide, which you might have seen before already. Martin-Löf type theory is essentially a formalization of realizability. So a type is, or a proposition is identified with a type or set or collection of its proofs. And this is well known in constructive logic. There it's known under the name Brouwer-Haitink-Kolmogorov interpretation. Essentially it says a conjunction is Cartesian product. Disjunction is disjoint sum. Implication, that's the most important thing. A implies B refers to the set of all constructions turning proofs of A into proofs of B. Similarly, for a universal quantification, and in case of existential quantification, you say a witness or proof of exists X, AX is a pair consisting of a little a, so to speak, a solution of the problem, together with a P, which is a verification that A actually validates the predicate in question. But in the original Haitink-Kolmogorov interpretation of intuitionistic logic, people don't say anything about equality. So this has to do with the fact that before the advent of Martin-Löf type theory, even constructive theories were expressed in the universal, fairly universal formalism of first-order logic, and there was no need for that. You just gave axioms for equality, but here you can form, that's what you read here. If A is a type in context gamma and X and Y are in A, you may form the type of proofs in inverted commas that X and Y are equal. Then you have the trivial part of equality, which says RAX, R for reflexivity, the proof that X equals X. Well, up to now everything's fine. But here comes a rule which we have seen yesterday, well, I guess on Ulrich's slides. So you might have seen it before. But it's a very non-canonical treatment of equality because usually you just have reflexivity together with a rule allowing you to replace equals by equals. So you have A of T, T equals S, you may conclude A of S. This is not of this form. And, well, this eliminator, or this formulation of type theory was enforced by general philosophical principle in Martin-Löf type theory that every type is defined inductively. So you just first say what is a type, then you have rules building up canonical elements. So there are just those. And that's an idea very prominent, say, in functional programming, is you want to define, you have a family C indexed over id A, and you want to define an element of C depending on this set, and you essentially define it by pattern matching. So elements in constructor form of identity types are guys of the form RAX. So to speak, a triple XX RAX is an argument in constructor form. The D describes how the function to be defined behaves on elements in constructor forms, and you say that's enough, right? So you just give a name for the function defined by this, say, sort of case analysis, but it only gets meaningful, or I mean, you get dynamics into it, because the very idea of Martin-Löf type theory is, I mean, if you do not want to execute programs, there is not much point in using Martin-Löf type theory. The really different idea is that you should be able to execute proofs, and here is the obvious computation rule. You have here the defined program. You apply it to an argument, but you only can reduce it in case the argument is in constructor form. So this is id A is inductively defined, is an inductively defined family of types. These are the constructors, and here are the eliminators. So if you write it down in an ordinary functional language, it looks a bit more friendly, and in some of something like ACTA or similar type theory-based supporting systems, you would do it this way. But that's, so to speak, the usual formulation when you use the official syntax of Martin-Löf type theory. So, yeah, using this, so the first exercise you do, yeah, is to prove the following thing. Maybe I should write it here. I should write it here. So you have E is a proof that A and A prime are equal, and from this you want to get the function from BA to BA prime, and let's call this wrapper E. So, yeah, I should maybe say that in context X of A, Bx is a type, yeah? Then the point is, you look at constructor form, then A is the same as A prime, I mean syntactically, and it doesn't depend on the canonical proof RA. From BA to BA you get via identity, and then applying the eliminator allows you to do what? Yeah, to generalize this to here. So this is REPL E. It's morally a J of id BA, so the identity on that here. That's what I meant with REPL. So I now have to look where I have, here is the pointer, right. Good, good. So using J, besides this replacement thing here, yeah, you can prove the usual properties of equality. So this is transitivity of equality. So if x equals y equals z, then x equals z. And inf A is if x equals I, then y equals x. So you can, it's an easy exercise to find such terms using the eliminator. And now you can do something, that's a particular feature of type theory, which normal syntaxes don't allow you to do is, namely you may ask whether proofs are equal, right? In type theory, you can do this because you may iterate the identity types. And so you can, for example, do the following. You have a proof that as f proves x equals y, g proves y equals z, then that here, of course, should be an h, sorry for that. So if I prove h that z equals u, then you can compose these two gadgets in two different ways. But again, using the eliminator j, you can prove that the result is the same, yeah, independent of the order how you apply the composition function. Similarly, you can prove that idx, we write here idx for Ra of x because it will turn out as sort of an identity morphism in the type considered as sort of a category, yeah? So this says idx is a neutral element. And finally, we also can say that the inverse of f is both right and left inverse to f. Well, the point is, these equalities here, yeah, are the equal only hold in the propositional sense. So I think it was addressed before. But the really confusing thing about type theory, and it's better to confess it openly or warn people in advance, is that you have two different notions of equality, and that's a real barrier for most people because equality is equality. That's what most people think. But here you have a judgmental equality. That means you have a judgment that in context gamma t equals s as elements of A, versus a so-called propositional equality, saying that in context gamma, t and s are equal, meaning that you have some term E of this type, right? And from here, from judgmental equality, you get to propositional equality. I mean, the point is type theory is a changing beast, yeah? Historically, one had a treatment, as I described it, with this notion of equality. Then in the 80s, people were using a judgmental equality. So when you add this thing here, you avail yourself of a rule called equality reflection, saying when T and S, the proposition that T and S are equal is witnessed by some E, then there also holds a judgment. It's very natural to postulate this because there is just one notion of equality. And what I think is that most people would be glad to work in extensional type theory. But the problem is, and this was observed in the early 90s, that adding equality reflection, that you don't have this complicated J at all. You have no eliminator, but you have just such a guy. Then type checking is undecidable, and that's bad news for implementers of the theory. But this is, in my eyes, a strong pragmatic reason why you can't always get what you want. So, I mean, you would like to have extensional type theory because it's closer to the kind of thinking we are used since Euclid. But on the other hand, if you adopt to this traditional pattern, then type checking gets undecidable. So in my eyes, it's a purely pragmatic reason why there was a move back. So first intentional, then extensional, then type checking undecidable. They moved back to that. Of course, a pragmatic failure, in my eyes, is a very strong argument, but it doesn't prevent people from inventing some philosophical reasons why it's good that you cannot get what you want. Yeah, but that's a question of discussion. You know? So, good. Yeah, what do we find? Here you see again on the slides written out in detail this REPL A, E, yeah? And then there are some further exercises you may want to do is, one can show that the equality, so you have a family, you have proofs that A and B are proofs that A and B are equal as elements of the universe. This gives rise to a map from A to B. So it means that, I should have said the following before. If you go back to here, then this looks like every type is a groupoid, right? Where the objects are the elements of the types, the morphisms are the elements of the it types, and the groupoid constructor are some algebraic operations which can be defined in terms of J. But this suggests that a type is a kind of groupoid, and this here says if you take the universe as a groupoid, then the equality proofs between elements of universe act in, you can show that replacement, REPL id is id, that REPL is functorial, and what I've shown here is you always can show that reindexing along E and reindexing along inverse E are mutually inverse in this sense here, right? So it's, most of you do know what is a group action. This would be a groupoid action, right? But the equalities here, you do not say that REPL E composed with REPL inverse E is actually the identity. You just say it's pointwise the identity. Because, intentional type theory is called intentional type theory. A better name would be non-extensional type theory. What you cannot prove in this series is that functions that are pointwise equal are actually equal. Right, and therefore when you formulate the notion that something is an isomorphism, meaning a function has got an inverse, you can express this in stronger and weaker ways, and this is sort of the weakest way, right? Good. Yeah, anyway, here comes what I said before already, here written out in detail. So, the availability of identity types and certain derived operations on them, which you can express just using this single at the beginning, somewhat mysterious eliminator J. Every type A is actually an internal groupoid, where the groupoid equations are not holding in the sense of judgmental equality, but rather in the sense of propositional equality. That means there is not just one possibility of being equal, but you construct a particular term exhibiting in which way they are equal, and this is strongly reminiscent of what you observe fairly early in category theory, where when you consider categories and functors, and already Eilenberg and MacLean defined natural transformations. That means Hom AB, when A and B are categories, itself forms a category. Such guys are called two cells. That means, so 0 cells are object, 1 cells are arrows or morphism, and 2 cells are morphisms between 1 cells, right? And there may exist more than one, yeah? Right. It means what the syntax of type theory already provides you is an analog of higher dimensional category. So higher dimensional category means you have morphisms of dimension n, and as soon as they have the same source and targets, there are cells, n+1 cells between n cells, which, well, in general it's just a morphism, but they could be isomorphisms, and there could be different isomorphisms between 2 cells. So what I want to state on this slide is simply that the syntax of intentional type theory provides you some material which is strongly reminiscent of higher dimensional type theory. And secondly, that the equalities are not holding in a strict sense, but those equalities, so the point is that this term and this term, they are not judgmentally equal. They are only equal in some sense as exhibited by such a term. Right. Good. Yeah. Now I'm recalling the Groupoidmodel, or rather telling you how we arrived at that. Right? I mean, type theory allows you to ask questions which people didn't formulate before, namely, because now so equality proofs are not something you can speak about. They are on the meta level. So when you do ordinary mathematics, you cannot ask whether two proofs are equal. I mean, philosophers do this. It's a difficult question, but a mathematician does not sensibly ask. So you will not find a theorem proof P equals proof Q, because there are no precise criteria for that. But here you can formulate it essentially in a formal way. And you see, I mean, I began to study those things after having finished my thesis on extensional type theory. That's a much simpler sort of thing, where there is no difference between these two notions of equality, and I tried to make sense. So the situation was, when I'd finished my thesis, type theorists came telling me that it was the wrong type theory. Extensional type theory is wrong. So this was a bit disappointing, so I tried to make sense of what really intentional type theory is. And in all, I mean, first of all, one should state this quite clearly, because it's getting forgotten nowadays. So if you read too much hot literature, you get the impression the only real interesting models of type theory are those which of intentional type theory. That is quite, I mean, this might be okay as a subjective statement. I'm interested in that and not in the other things. But there are plenty of models of extensional type theory. Every elementary topos is a model of type theory. The other thing was that using techniques from proof theory and giving them a semantical slant, so-called realizability models, were models of extensional type theory. And in all these models, identity types are interpreted as a naive person would do. It's empty. Id ATS is empty. If T and S are different, and if they are equal, there is just one element, because there is just one way of being equal to itself. Yeah, right. But the question was whether in intentional type theory you can prove or disprove such a statement, namely, all proofs F and G that X and Y are equal, are they equal, at least in the propositional sense? So the point was that in the early 90s, all models one knew validated this principle, uniqueness of equality proofs. And so I believed it should be provable somehow. And actually it can be done if you stick to the same inductive definition as before. Yeah, it's here. Yeah. Here you have just one eliminator. But what you may do is you take your family id and diagonalize it. You just consider the family id AXX. And this also can be endowed with an eliminator, which moreover has a computational meaning. So you may, I called it K just because it's the next letter after J, and it's as inspired a terminology as is J, so it just took the next letter. So you can have this. So this is an eliminator for the diagonalization of identity, and this has perfect computational meaning. Here you have the eliminator formulated precisely, and here you have the computation rule. There is no problem whatsoever in giving an operational semantics to that. Well, that's how far I came in my attempt to explain intentional Martin-Löf type theory to myself, but of course it was unsatisfactory because we could not decide the question, is UEP provable or not in Martin-Löf type theory? And then in discussions with Martin Hofmann, there appeared this idea, namely we saw that internally identity types endow types with the structure of a groupoid, to turn it around and to say, yes, why not interpret types as groupoids? Yeah, namely the objects of the groupoid A are the elements, and id AXY is just a Hom set. Yeah, and then if you just take a non-trivial group, it has just got one object, but a lot of different proofs that this one object is equal to itself. So take any non-trivial group. This clearly makes uniqueness of equality proofs wrong. Yeah, okay, that was a basic insight. But then one had to do the following, namely to show that groupoids do form a model of type theory, and that's essentially what we did in this paper from 1984. Okay. But groupoids are not as bad as syntaxes. So that's one of my favorite formulations. I mean, it's something, yeah, when you do independence proofs, there is something you cannot prove, and you want to find a model where this thing you cannot prove does fail. In this sense, I use the term, it's as bad as syntax, because a model refutes something which you cannot prove. So, the groupoid model is still too good in the following respect. Namely, when you take the groupoid model and you take here AXY, then this AXY is just a set or a discrete groupoid. That means uniqueness of equality proofs always holds when you have iterated equality proofs, right? Iterated identity types, right? And therefore we thought it actually should be infinity groupoids, yeah? So you have always for n cells, you have n+1 cells, and in general there should be more than one. And the second thing was strict omega groupoids are also better than the syntactic reality, because in groupoids, these laws we have here, these laws we have here, I mean, it's better because these equalities are judgmental equalities, right? So not having these equality as judgmental equalities means that, for example, that associativity for composition and so on doesn't hold on the nose, but is just witnessed by a cell of a dimension higher by one. Yes, right? So we thought actually models which are as bad as syntax should be something like weak higher dimensional groupoids. But then there was this question we have here. We both did not know what's a good notion of weak higher dimensional groupoid. I mean, those days, I was often, I do this even nowadays, but attending categories meetings, and there you typically would could hear talks about 1 hour, the whole hour is devoted to explaining one notion of higher dimensional categories. That was a bit frightening for me. I don't want to work with something where it takes 1 hour to explain the basic notion. Well, that's the reason why for quite some time I didn't think about it. All this higher dimensional stuff is too frightening for me. But then there was, yeah, so this is, I will describe how we and mainly other people came towards infinity groupoids. So we knew already before that this would be the real thing, but I at least was not knowledgeable enough and not diligent enough to absorb all this stuff. But there was organized in November 2006 a meeting where category series, homotopy series, and type series should meet. And already this time, as it was also announced that Vladimir Voevodsky should show up, but for some reason he was prevented from coming. But people have heard that there is an unpublished report with the somewhat perplexing title, Homotopic Lambda Calculus. So I think this rumor already triggered this meeting there. So I was invited to give a talk there and wanted to tell a bit more than the almost 10 years old results Martin and I had. So I tried again to find out what you can find in the literature about weak higher dimensional groupoids. And then I found out I just attended the wrong talks because so what I came across was some little paper by André Joyal about what he calls quasi-categories. And they are a more general thing than so-called Kan complexes, which I will define on the next page. And there, at least the definition of what a weak higher dimensional groupoid is something which you can write down in 2 lines. Good. Anyway, I familiarized myself with a kind of mathematics which was essentially developed at the time I was born, so end of 50s, early 60s, and I learned a bit about Kan complexes and Kan fibrations, and those guys take place in the topos of simplicial sets. S stands for simplicial sets. Delta is just the small category of finite ordinals different from 0 and monotonic maps between them. So it's a simple pre-shift topos. Good news. That's an easy thing. And on the very soon you will say how you define the notion of a Kan complex and a Kan fibration. What also happened approximately at the same time, so as I know, it's always dangerous to say such things, but anyway, following a suggestion of Ike Moerdijk, who essentially said that maybe something like model categories, you have path spaces and maybe that's related to identity types. He uttered this, he made this suggestion in some discussions. I wasn't present there, but that's what I've heard. And then Audi and Warren, I think it was in early 2000 at Mittag-Leffler Institute where those things took place. Anyway, Audi and Warren took up this suggestion and wrote a nice paper showing how you can describe the interpretation of identity types in so-called Quillen model structures, right? You don't need to know properly what Quillen model structures is. I show you as much of them as one needs for interpreting type theory, right? But independently, presumably earlier, but there was just this unpublished draft on homotopic lambda calculus. He also suggested to interpret type theory in simplicial sets, and he went much further, namely in formulating the univalence axiom. Okay, and the univalence axiom, we will see this later on, is essentially saying that types are equal if they are isomorphic. I mean, that's a connection. So a slightly imprecise but fairly descriptive formulation of univalence is the title of the talk without a question mark, just with an exclamation mark, so to speak. So, well, some of you might know this, but I give a very short recap of what simplicial sets are. So delta is a category of finite non-empty ordinals and monotone maps between them. We write square bracket n for the ordinal m plus 1. The maps of delta are, in old literature, you can say the maps between them are generated by degeneracies and face maps. So this guy here is monic, it's 1-to-1, and it omits the index I, and this here is epic, it's onto and repeats I. And from these two classes of maps by composition, you can generate arbitrary monotone maps between finite non-empty ordinals. Yeah. Right. Now, well, we write simplicial sets for these preshift topos. We write delta n for Yoneda n. Then, yeah, this here, delta I of delta n. Delta I is maybe, yeah. Yeah, this is the subobject of delta n. You think of delta n as a simplex. What I should say before. I mean, because this explains things quite nicely. So you have a map from delta to spaces, a category of spaces, and this is geometric realization. The point essentially is it interprets the n-dimensional simplex as a real Euclidean simplex. And similarly, you can do with morphisms. Then here, you have the preshift topos. Here you have Yoneda, and there exists a unique up to isomorphism extension, which is written R, right? Geometric realization. That means you have a functor which interprets your simplicial sets as spaces. In a sense, a simplicial set is a blueprint for building up a CW complex, right? Yeah. Right, so here is the boundary. The delta IN is you remove the interior and the face opposite to vertex I, yeah? But what's really important for us is this lambda nk. People call it the horn. I mean, yeah. What is a horn? You have a simplex. You remove the interior and one side, and if you remove the face opposite to vertex I, this is called the ith horn, right? Good. Now, I give you a few pictures of horns. So here you have a horn where you have just one morphism and another one. So this is a kind of blueprint for a composition, yeah? Okay. There are two other horns where you remove these guys. This is not for composition. Yeah, these are non-inner horns. So there is one inner horn and two outer horns, if you want. And now, yeah. So the definition of a Kahn complex, and this is very old. It says something. So a horn in a simplicial set X. Is just a morphism in simplicial sets from this guy here to X. And a Kahn complex is a simplicial set X such that whenever you have a horn, yeah, this horn can be filled. That means for any H from here to X, yeah, it extends to the whole simplex. Yeah? And it's important that this extension needn't be unique, it just exists. So if you require this extension property for all horns, then you get the notion of weak higher-dimensional groupoid. And I mean, that's what I mean. This definition is very palatable. You don't need a whole lecture to explain it. Now, just for information, requiring this horn filling property. So one says, so H is a horn in X, and it can be filled up to a horn H bar, to a morphism H bar. When you require this only for inner horns, then you get the definition of quasi-categories, and when you require this filling property for arbitrary horns, you get this age-honored notion of a Kahn complex, yeah, developed by Kahn. By the way, this thing here has got the right adjoint, very well known in topology. It associates with a space, a so-called simplicial complex. That means with a space, you can associate a simplicial set which, and the simplicial sets you get this way are up to equivalence precisely the Kahn complexes. So that is the reason why this notion was developed. And by the way, this adjunction here was, I mean, I didn't know this because, like many people, I didn't read the original papers, but Kahn's 1958 paper had this example of the adjunction between realization and simplicial complex, the motivating thing, which is no surprise since he was a very important algebraic topologist. So in later texts, which I had a look at, this didn't show up as a motivating example for an adjunction. Yeah, now there is something like classical Quillen model structure on simplicial sets. So I just give you an impressionistic impression of what it is, just to have those things available which we need for interpreting type theory. I said this already. There is an obvious functor from delta to the category of spaces, right? And this here, the left Kahn extension. Well, I don't explain what it is, but the point is, in every pre-Giff topos, every pre-Giff can be obtained as a co-limit of representable ones. This guy prescribes the behavior on representable objects, and so there is up to isomorphism just one co-continuous functor extending this. Yeah, I'm not defining you the general notion of what a Quillen model structure is, but I say what is the so-called classical Quillen model structure on simplicial sets. So it's given by three classes of maps referred to as fibrations, co-fibrations, and weak equivalences. So weak equivalence, in a sense, they are that object in which people are really interested in, because usually you define a weak equivalence is a continuous maps between spaces such that from a homotopy point of view it's an isomorphism, meaning applying the nth homotopy functor to this map F always gives rise to an isomorphism. So weak equivalence means it's a map between spaces which from an algebraic point of view looks like an isomorphism. And the other gadgets are just hanging around to axiomatize the behavior of W. Right. In this particular case, C is very simple. It's a class of monomorphisms. W is a class of weak equivalences. F is a class of Kahn fibrations, and I will tell you what they are. Yeah, okay, weak equivalences are those guys whose geometric realization, so a weak equivalence is a map between simplicial sets whose geometric realization is a homotopy equivalence. That's something different from weak equivalence. So usually say F is an isomorphism if there is a map in the opposite direction, such that both composita are equal to identity. Being a homotopy equivalence just means both composita are homotopic to identity, yeah. And Kahn fibrations, I hope I was a bit too fast. Here you find the definition of a Kahn fibration. It's like that. So if B is 1, yeah, then if for the case B is 1, this says that E is a Kahn complex. It's most natural to consider here arbitrary maps instead of just terminal projections, yeah, okay. So morally, Kahn fibrations are B-indexed families of Kahn complexes, which in addition are well behaved, right? Now we have, now I've described you, or recalled for most of you, what are the three ingredients of the classical model structure on simplicial sets. Now the point is, as we have seen, for example, this morning in Page and Orr's talk, I mean, to interpret type theory, you give a category, which is simplicial sets here, and you come up with the notion, with a class of maps called display maps traditionally, which are closed under substitution and have a lot of other closure properties. But in any case, I mean, it's obvious that confiberations are stable under pullback. So this provides you with the possibility of modeling type theory. As soon as you have a pullback stable class of maps, you can say this is my notion of family of types. Right, and you can do this. Here they are called confibrations and not display maps, and they are defined, because they are defined by a weak orthogonality condition, being right orthogonal to something, it's obvious that F is closed under composition, and one also can show that it's closed under dependent products, because, well, when you know what dependent products in a category with pullbacks are, it essentially means pi sub F, the right adjoint to pullback along F. And it's not easy, it's not difficult to see that pi, that confibrations are closed under pi if the class C intersection with W, I mean monomorphisms which are at the same time weak equivalences, is stable under pullbacks, stable under pullbacks along maps in F. But this fact here you find in the respective books, but the proof is not too, it's fairly non-constructive. You need something called minimal fibrations. It's heavily classical. But in any case, since we have here, we can interpret, so you take simplicial sets, and families of types are given by confibrations. Therefore, you can interpret already dependent sums and dependent products, and you also can interpret identity types following the recipe as given in Audi and Warren's paper, which was available as a preprint those days. Yeah. But one should say, yeah, how new is this model compared to the normal set theoretic model? I those days was not too enthusiastic about it for the following reason. Namely, there you have here global elements as a functor from simplicial sets to set, and this has got the left adjoint, which just sends a set to the constant presheaf with this value. Then the point is that this delta is full and faithful, and moreover preserves the locally Cartesian closed structure, which is a posh way, a complicated way of saying as long as universes are not involved, the simplicial set model is not different from the so-called naive model of type theory in sets. And this applies to actually all models of homotopy type theory available by now. Yeah. Okay. So as long as we haven't got universes, nothing new, but maybe that's not so bad. I mean, it depends on what you want. So if you are a constructivist, that's bad because it interprets a universe-free part, one could call this elementary type theory, in an absolutely unsurprising way. But you also could, what is bad for one person can be good for the other one. I mean, you have a model of type theory which interprets basic mathematics as usual, like in sets. Yeah? But only it differs from ordinary mathematics, say set theory, only in the way it deals with universes. We have seen this partly today, but I briefly recall this. So I recall Audi and Warren's way of how to interpret identity types in Quillen model structures. As a matter of fact, you need much less, namely so-called fibration categories, where, I mean, the point is when you have these three classes of maps, I think it was mentioned in some talk today, it gives rise to two factorization systems, weak factorization systems, and only one, namely this one here, C intersection W and F, that's relevant for type theory. Yeah. The other one is there, maybe important for the homotopy series, but for interpreting type theory, it's not relevant. So, I mean, actually, most of what you find in Audi and Warren's paper applies to vibration categories. So the point is, how do you interpret identity type? So you have A, it's a type A in context gamma interpreted as I. So what you do is, well, you interpret identity as a diagonal, that you do it in case of types when this is 1, but usually, if you are in well-behaved situation, everything is stable under slicing. So you take here the product of A, and this little delta sub little I, that's just a diagonal in the slice category. Yeah. So you interpret identity types just as you usually do. In most models which were known, say, till the mid, around 2005 or so, right? And then what you do, you have seen this today, you take the diagonal, and there is a property of equivalent model structures, namely that you can factorize any map into a map in a weak equivalence, which is also a cofibration. They call this an anodyne cofibration in the respective literature, and the vibration. So Pi, that's a vibration, and this is a monic weak equivalence, right, as written here. Now, if I is terminal, then you may, in this particular case, choose. I mean, this factorization here is not unique up to isomorphism. That's alarming for the category theorist, but sort of normal for the homotopy theorist. But you can choose this, yeah? The whole thing, I mean, the whole definition of quasi-categories or of complexes is not very algebraic because it's not in terms of operations, just in terms of these filling properties, and there you have existential quantifiers without any choice, right? Now you may choose this as A to the delta 1, so delta 1 is a one-dimensional simplex, a line segment, and RA you define as this one, you send an element of A to the constant path with that values, and here you give how it's depending on A times A, yeah? And this factorization can, as this observation can be easily adapted to slices over I, yeah? Because we are in a locally, in a topos, so in a locally Cartesian closed category, meaning that in particular, if you take a slice of your category, it's as good as the original thing. In particular, you have got exponentials in the slices. And here, I think we have seen this already, or some of you have seen this in Page's talk. This filling property allows you to interpret elimination. So you have here id A, we can consider this square, where this is the identity. This P sub C is a vibration interpreting a family C indexed over id A. And here we have RA, and here we have a D, which in a sense prescribes the behavior of the function to be defined on constructors. And then because anodyne cofibrations are orthogonal to Kahn fibrations, we have a filler here. So this commutation of this triangle tells you that this is a section. So J of D is an element of C, and this here corresponds to the validity of the computation rule for the universe. But there is a problem, and those days there was quite some discussion about those things because, you see, if you work syntactically, you're used to the fact that, I mean, when you substitute into a formula, I mean, textual substitution by its very nature commutes with every logical construction. But that's not so clear when you interpret things. And therefore, when you formulate notions of models, so it's not enough, for example, to have right adjoints to pullback functors. They also have to validate a so-called Beck-Chevalley condition, which is a requirement on this class of display maps guaranteeing on the semantical level that substitution commutes with a quantification in the expected y. But and I mean, this was observed at the time when people first considered models of type series, or from mid-80s to early 90s, yeah, that the importance of the Beck-Chevalley condition is, I mean, it's absolutely intrinsic for being able to interpret type theory. But here, right, you choose such fillers, the whole thing is living in the slice over I. You may have a map U from J to I. You pull back this situation here, right? And then when you pull it back, this should correspond with your choice. I mean, it's related to this problem. So an earlier incarnation of this so-called coherence problem is, can you do choices in a functorial way, right? So can you choose those fillings in a functorial way? For example, can you also choose pullbacks in such a way when you put two canonically chosen pullbacks side to side, then the ensuing rectangle is again a canonical choice. Yeah. So there is no guarantee for that, but there is a nice hack for achieving this. This is what I suggested to Steve and Michael when discussing this issue up in Uppsala in 2006. And it also, but the same trick essentially, you find in Voevodsky's notes on notes on type theory. I think it's still available on his homepage. But the trick is the following, and in a sense, it's a very canonical one, yeah? So you are working in a generic context. That means, so you have some universe set. This need not yet be split, right? So consider this context. That's a generic context. You have A and Z. You have a family C, indexed by that. You have a D, which is a section when you restrict along R or along the diagonal. Yeah, but now clearly, relative to this generic context, you can consider A, C, and so on. That means if you split this thing here, if you split here in the context I, yeah, and you instantiate I by this generic context, you can split whatever you want, but you split all situations at the same time. And the special instances you just get by pulling back along maps into this generic context. Yeah. So that's a trick. In a sense, it's a cheap trick which allows you to solve coherence problems in a simple way. So I suggested it those days. You can find it in a different disguise in these unpublished notes of Voevodsky. And maybe the latest, an up-to-date place where to read about it is the paper by Peter Lumstein and Michael Warren, the local universe method for splitting, or an overlooked method for splitting, yeah, which essentially uses, yeah, this trick. So this is global universes, yeah. So that means you're working just in one context, and yeah, you can generalize this to have many universes, and what you get then this is nothing else but the so-called left adjoint splitting of Giraud, because the point is, a model of type series is essentially given by a vibration, as we saw this morning in Page's talk, and then not every vibration is split. That means reindexing can be chosen to be functorial. And already from a work of Giraud in the 60s, or at least you find it. If you are really lucky, or if you are very patient, you can find it in the 71 book by Giraud on cohomologie non abelienne. So he constructs a left and a right adjoint to the functor for getting the splitting, as a cleavage of a splitting of a vibration. So anyway, so this trick here, this was not clear to me when I considered it as a particularly cheap trick, but I like cheap tricks. I like simple tricks, maybe not cheap, simple tricks. But it was not clear to me those days in which sense it is related to the so-called left adjoint splitting of Giraud. But you can read this in detail in the paper by Lamstein and Warren. Right, so with some, maybe not very elegant, but working trick, you can solve the problem so that category theory is not as coherent as syntax. Huh? Yeah, but a quick one. I've just 20 minutes later.
Yeah, I wonder, this morning you said that actually one doesn't need to split usually if one looks at a concrete example, because one can find an interpretation which is split by itself.
Yeah, here this is speaking about the general situation.
Yeah, sure. But when you started with just wanted to interpret identity type in simplicial sets. And simplicial sets, I think you can just find...
you can do the following. You can choose id A as A to the I, exactly. But it doesn't help you with the J. I don't know of any canonical way of filling, of finding the diagonal fillers.
Okay.
Because it's usually provided by what's known as the small objects argument. It's a huge transfinite construction. You cannot use this whenever you use J. Yeah. Here is coming an important thing, namely universes. So that's also, in a sense, very old little observation by Martin Hofmann and myself, which it was originally not motivated by question of homotopic type theory. That was something independent. The question is, you have U as a Grothendieck universe in set. So we had a little note of lifting Grothendieck universes to pre-shift categories. Yes, you can do this. By the way, a Grothendieck universe is a precursor, at least temporarily, of the type theoretic notion of a universe. So it's something like a transitive set which has even a bit more closure properties than required by being a model of set theory. Anyway, I'm not explaining this. Now, from a Grothendieck universe, a set theoretic gadget, you can construct a universe U, where U tilde is what other people write EL. Okay? So U is the universe, and that's the family of types turning an element of a universe into a type. And the corresponding map we describe as P sub U. And we can do this in any pre-shift category. And as very often in category theory, you are very lucky because Yoneda guides you what to do. So if you follow the generally very helpful advice of Yoneda, so you end up with the following thing. I don't have time, and it's not written here, but this is not an ingenious invention, but it's just following what Yoneda lemma suggests you. So U over I are just pre-shifts over C over I, yeah, taking values in the Grothendieck universe U. Here the font of the U is very important. When it's calligraphic, it's set theory. The Roman thing is just the type theoretic universe. And reindexing is achieved by precomposition with sigma alpha. So when alpha is a map from J to I, you just precompose with sigma alpha, and sigma alpha is composition with alpha, right? Fairly traditional stuff here. And the presheaf U tilde is defined as follows. So U tilde I consists of elements A, which are so generalized elements of U at stage I. You now must recall what A is. It's a presheaf over C of I, and the little a is just an element of A of id I, right? And here is, you need not understand this formula here, but it's also very systematic. This gives the morphism part of that. And this can be derived in a systematic way. So I also wrote a little paper called Universes in Toposes, where I extended this observation of Martin and me. It not only works for presheaf toposes, but also for general Grothendieck toposes, right? So that's how you have how a set theoretic universe, a Grothendieck universe, lives up to a type theoretic universe. And one easily checks that this map PU, yeah, is a generic family. So this map PU has small fibers, small in the sense of U. So a set is small if it's equivalent to an element of the Grothendieck universe. And every U small map can be obtained as a pullback of PU. Yeah? Okay? That's how one can make universes. So simplicial sets are presheaf topos. So one could use this construction of universes in the particular presheaf topos at stake, but there is a little problem. Yeah, maybe I write something here. So the whole thing is based on an old observation, essentially telling you that when you have a presheaf topos C hat, and you take the slice over X, then this guy is a presheaf topos again. Namely, you take the category of elements of X and take presheafs over that, right? I mean, that's really what's behind that, because you can instantiate for X such a delta N, yeah, a representable object. So, but now the point is, in the original definition, you took all presheafs over delta over n, including those which are not confibrations. But the elements of the universe should be a type, so the natural thing is you restrict to those presheafs psi such that P sub A is a confibration. Well, what is P sub A? It's applying the Grothendieck construction, turning a presheaf, yeah, over delta over n into a map to delta over n, right? Good. So that's a way how you can cook up a universe in simplicial sets. What is easy to see is that families of simplicial sets with U small fibers are closed under sigma pi. It's also generic for such families, but what is really difficult, and I couldn't do this, but well, I don't know where you can read it, but it's in some talks by André Joyal, this was provided. He used a lemma he had in his book, in his to-be book with Tierney, and added a further one. Anyway, there is a proof showing that U is a Kahn complex, but that's the hard part of it, right? Right, and for this reason you can interpret type C. You have a universe which is closed under the respective type formulas. I've just, yeah, a bit more than 10 minutes, so let me look. Yeah, maybe I skip these things because you might have heard it anyway. Okay. One little observation, which is interesting, and you don't see it that often. I mean, Voevodsky originally, but that was kind of a historical accident. I mean, because he learned type theory via attending a course on Koch, and Koch has got an impredicative universe. So I just want to say a little bit about impredicative universes. So if you take P01, and I mean this in the sense of the set series, you have the empty set and the canonical one-element sets. If you take this set, curly P, instead of a Grothendieck universe, you can perform the same construction, right, as before, replacing curly U by curly P. And what you get then, so prop N consists of all monos, which are confibrations, right? And one knows that these are trivial. So what I want to say is, if instead of a Grothendieck universe U, you take a pocket format universe, no? Empty, non-empty, and you require all those things to be confibrations. So the point is, a mono, a subobject of a representable thing, is a confibration if it's trivial, meaning either the identity or zero. That means if you interpret from calculus of construction an impredicative universe in there, in this model, then you get something, again, very boring, namely, I mean, I said before, as long as you haven't got universes, the simplicial set model is excessive boring. It's like set. But if you interpret the impredicative universe, it's just two-valued logic. And so when you formulate notions like weak equivalence or things like that, as here, you might have seen this, then in your logic, you do not use prop. So without saying too loudly, so silently, I mean, also people were starting from formalizing those things in prop when you form those things, formulate those things which are characteristic of homotopy type theory, like contractible, H-fiber, and things like that, right? Then this does not live in prop, right? Because prop is too boring. Yeah. So what I essentially want to say, you must not use the existential quantifier as suggested to you by prop. You have to use the good old sigma of Martin-Löf type theory. So I wanted to say the impredicative thing, there is at least one person, presumably more, who's strongly opposed to impredicative things. That's not my attitude, but I say, I mean, you cannot use prop for formulating the axioms of homotopy type theory as here. Yeah? So, yeah. Where is it? Ah, yeah, I said, yeah, here. Yeah? So you say for all x, y in your universe set, the canonical map from it to weak equivalence is itself a weak equivalence. So here you don't see what you have actually used. But what I want to say is you're using sigma and not the existential quantifiers as provided by prop. Good. I want to ignore this slide. Instead, okay, so the point is, people have proved, so there is an unpublished paper by Voevodsky, Kapulkin, and who was Warren, presumably, anyway. No, Lamstein, Kapulkin, and Voevodsky, who prove that this simplicial set model is actually validates univalence, right? But there is a problem with that, because, I mean, the point is, if you formulate univalence like I did here, you do something which you wouldn't have dared to do in the old days. I mean, if a type series is in the room. Namely, you just add a constant of a certain type without providing it with any computation rules, right? Yeah. So the problem is, it's certainly consistent to add weak equivalence, and the simplicial set model does prove it. But this way it loses all computational meaning, because you postulate a new constant of an appropriate type called UA, and then you can build up natural numbers possibly containing this UA, and you cannot further reduce them. So you get rubbish, you get garbage. Not every term, every closed term of type NAT would reduce to a natural number. So good. So here, this is a summary, and I also formulate a few problems or interesting things to look at. So anyway, we have organized the simplicial set model into a model of type theory, and Voevodsky and collaborators have shown that it is univalent. So here, yeah, the computational meaning of the univalence axiom. That's a very difficult thing, but there has been recent progress by Thierry Coquin and some collaborators. So they were using not only cubical sets like simplicial sets, but the geometric figures are not simplices, but instead cubes. But it's not only that. You have a refinement of the Kahn-filling condition, namely that it works in a factorial way, right? So anyway, using pre-sheaves over a category of cubes, I even can tell you what the category of cubes is. You have so-called De Morgan algebras, that's distributive lattices with an antimorphism, and yes, obvious morphisms between them, and you take the algebraic theory of De Morgan algebras. That's your site instead of delta. And in the pre-sheaf topos over it, you can give an interpretation of type theory which proceeds in a very different way. So identity types aren't anymore inductively defined, but you introduce a lot of different things. Something like fillings, composition, where composition means you have an open box and you add a lid on it, or maybe you also fill it, and a further slightly mysterious thing called gluing. So the point is, you analyze a particular model, namely cubical sets, and avail yourself in the syntax of things which a type series never would do. Yeah. So you invent some new syntax reflecting something which exists in the model. And this way, yeah, and there is still an interval there. So id A is still A to the I, but now the new thing is, so the I is not a Kahn complex anymore, it's still a pre-type or a type deuxième class, not really one. You may use it for describing passes. So anyway, they came up with a so-called cubical type theory whose syntax is inspired by this particular model. And for this, there you get function extensionality is a trivial consequence, and with much more effort you can show that univalence holds there, but not just by postulating it. And presumably this new syntax, which is not very meaningful from the logical perspective, you can't understand it without having this particular model, namely the cubical sets model in mind. Yeah, this presumably, they have endowed it with conversion rules, and they claim, and it's not unlikely, that this has normalization property. So in one particular case, but making a lot of arbitrary choices, one has come up with a type theory considerably different from original Martin-Löf type theory, where univalence holds and has got the computational meaning. And it is the case, so you can, when you have, say, type theory together with the univalence axiom, you can translate it into this cubical type theory. Right. So that's, I mean, keeping the computational flavor when adding univalence, I think this was, or still is, one of the hardest problems in the whole business. And there has been made considerable progress by Thierry and collaborators. There are other two things. I mean, I guess there are much more things, yeah. I'm not mentioning hits, or higher inductive types in particular, because I don't know too much about them. But what is a flourishing subfield of homotopy type theory is, as we saw in Ulrich Buchholz's talk yesterday, doing synthetic homotopy theory. Not working in spaces or simplicial sets directly, but using the identity types as a synthetic notion of paths. There is quite some activity, and yeah, quite a few theorems from algebraic topology have been reformulated in a syntactic way. I want to end with that aspect, which I find interesting, but is the one where there has been least progress. Then there is something, I've briefly mentioned quasi-categories. These are weak high-dimensional categories where all cells from dimension 2 onwards are isomorphisms. And if you impose a few further axioms, there is a notion of a so-called infinity topos. These are particular quasi-categories. And some people say it's obvious how to interpret type theory in infinity topos. I mean, the motivation is sort of understandable. I mean, internal language has been a useful, versatile tool in ordinary topos theory, and there is this dream that you can use the syntax of type theory for speaking about infinity toposes. But, so there is some progress, but there are also a lot of open questions, because what people have achieved, who did this, there was some discussion between Schulman and Sisinski, and there was a paper by the young Koch, so Joachim Koch, not his father, Anders Koch, and a guy, Gepner, a real algebraic topologist. I mean, what they showed, when you take an infinity topos, I can't tell you now what it is, then you find a representing model category. So you have this weak and infinite dimensional thing, but it's represented by something which is sort of a model of type theory, namely a category, together with a class of display maps. And what you can do is interpret type theory in the representing model category. And so this has been achieved. That's not bad. But there are two questions with which I want to conclude is, I mean, there are different model structures representing the same infinity topos, and they might be give logically inequivalent models of type theory. So this makes it a bit disputable whether it does make sense at all to interpret something like homotopy type theory in an infinity category. You can interpret it in a representing model structure, but presumably it's dependent on this choice of representation. Yeah, and now I better finish. Thanks for your impressive patience.
So we have time for some questions. Are there any questions? Yeah.
Okay, so can't you use your lifting universes work together with the work of Thierry and others on cubical types to get universes a la Russell in at least pre-sheaf infinity toposes? Right, because all infinity topos are localizations of pre-sheaf infinity toposes, and as far as I understand the state of the art, we know how to preserve having models under localization. So the problem is really having models in all pre-sheaf infinity toposes. But isn't it possible that your very own work could help us do that together with the models in cubical sets?
I mean, you can. I mean, very often, if you start from reasonable infinity toposes, you interpret in a category of preshifts, and then you can use this machinery. Yes, you can do this, but then this is not interpreting them in the infinite toposes itself. So, for example, I mean, if you take cubical sets and simplicial sets, are they really different as infinity toposes?
No, but I'm suggesting that you to take a presheaf infinity topos, right? You can interpret that as maps into, say, cubical sets. And
yeah, but there I don't know how to do it. So we do know how to interpret type theory in presheaf categories, in particular because we can split them essentially using this observation from the 60s, yeah? And this we do not know how to do in the case of infinity, even not of, when you take some category and take preshifts in the quasi-category of Kahn objects, yeah. Now, I wouldn't know how to do this. I mean, the only thing I understood, so I mean, there are people who simply say, it's clear you can do it without saying how to do it. There are the people who are more skeptical, so to some extent it's wishful thinking. There is only one suggestion in this vein where I could make sense out of it, at least why it should work in principle. So what they suggested, I mean, it's a bit bizarre in my eyes. You will form your opinion yourself. So they said, you interpret a type theory where you just have normal forms, and you have just normal forms, then you don't have to interpret judgmental equality, you see, because judgmental equality is not interpreted in a way as originally intended. It's not decidable. It's interpreted as good old equality of morphisms, whereas propositional equality is that those guys are homotopic, right? Yeah, now I sort of forgot what was the original question. Sorry. So
the question was whether, I mean, there's nothing like this trick. You said the reason you can't just take the category of contravariant functors.
I don't know how to split those k-valued preshifts.
Okay.
I don't know that. That's the point. Yeah. And you see, the question I'm asking myself, to which extent does the interpretation depend on which representing model category you're choosing? Now, well, it cannot depend, it cannot differ as long as you haven't got universes, because there you have this full and faithful LCCC preserving delta. So it has to do something with the universes. But I mean, the other thing would be to identify a part of type theory which is, so to speak, homotopy invariant. To identify a class of judgments where the meaning, which are equally validated when interpreting them in models arising from two different representing model categories. But that sounds to me as sort of hopeless, right? No evident candidates, right? But anyway, there is a big gap, and yeah, it would be nice to have type series and internal language of infinity toposes. So that's certainly something which is in the air, and some people are keen to do, but I haven't seen that much progress in this way. But there might be other things, for example, like hits, higher inductive types, but I myself don't know enough, so therefore I decided not to mention them too much.
Okay. One last
just a question about synthetic homotopy theory. I think what you say that it just holds for simplicial sets, right? Which is not the whole homotopy.
No, I don't think so. Because what they are doing is they're essentially using id-A. I mean, id-A for id-A xy is a set of passes. It's just what syntax gives to you. So you're working with an anonymous notion of pass, and you are not exploiting the specific features of any model. But I mean, what you could use is that id-A is given by an interval. I mean, is that the people doing synthetic homotopy theory, are they using that id-A is of the form A to the I?
Usually not. I mean, you could do that, but the usual elimination rule is just what you need usually.
Hasn't turned out as useful so far.
No.
But I've seen a kind of issue between Voevodsky and Auri, because Voevodsky, I think Vladimir told that there is no interpretation like in general homotopy theory, meaning, say, Quillen category. So what works for simplicial sets or for cubical sets, it's even he mentioned, he's not here to ask him, some counterexamples in say, general homotopy theory. So
I'm not sure.
I can tell you what my impression is. So I mean, most of the model structures considered describe the same situation. Yeah?
No, it looks like this, but maybe there is hidden.
And therefore some people think because there is just one category of homotopy types, it shouldn't make any difference. But it's not proven. Yeah? I mean, it could well be that if you fix, which hardly ever happens, some formal system called hot, yeah, then you could ask, is it, does it validate the same judgments in our sufficiently well-behaved Szysinski model structures, for example, which is a well-behaved class of models? So I don't know the answer. It must be at universes that it's different, but yeah.